So, could you begin by stating your name and what you do here at the university?
So, my name is Jim Bull, and I'm a professor in biology. I teach a course for non-science majors. It's in critical thinking. It doesn't overlap very much with my research, but the motivation for the course is really to help people know how to make decisions using evidence. The research I do is genetics and evolution. I focus on mostly on microbes, and it's a mix of lab work and some theoretical work.
So, what made you want to do that type of research?
Good question. I think when I was in high school, I never envisioned this type of career. It wasn't until I went to school at Texas Tech and I started working with professors there that I thought I might like to do this sort of thing. That is, just be a college professor.
Mm-hmm.
And actually, when I came to UT, I was working on evolution of sex determining mechanisms. And I've been here 5 or maybe a few more years, and I changed what I did, and I started working on viruses and more on genetics than I had. So the nice thing about this job is it gives you complete freedom to choose new problems to work on. It's really about problem solving.
Mm-hmm. So, before you came to your professor conclusion as a job aspiration, what did you want to be before that?
It could have been lots of things, I guess. When I was in high school, I could have imagined being a high school teacher. I could have imagined going into being kind of almost a mechanic type person in industry. So that was, I went to high school in the 60s.
Mm-hmm.
And back then they actually had shops in high schools. You could actually do things in some of your courses. So I liked woodworking. I could have imagined being a machinist, something like that. But I also knew I wanted to go to college, and then when I started that, I majored in biology, actually zoology, just because I like the animals, which is the wrong reason. But anyway, then I got there, and it's one of these things that just turns on a casual interaction. There was a new professor at Texas Tech who I'm still best friends with, and he's still a professor at Texas Tech, and he was a mammologist, and he was charismatic and had field trips and liked working with undergrads. Started working with him, and that's really what set me on the course I'm on.
So, as an undergrad, did you partake in any particular research?
Yeah, so actually as an undergrad, I was doing work on snake chromosomes. So this was in Texas. I'd grown up in Wisconsin. There isn't much exciting going on in Wisconsin when it comes to critters outside. So I love Texas. And he and I and another undergrad started a project on snake chromosomes. And by the time I was done, I had 2 publications. And that was, say, if you think you want to go into research, start it when you're an undergrad. Don't wait. So that it was great, and it was just sort of the combination of him. If he hadn't been there, I'm not sure I would have ended up doing it, right? It took a professor to show interest, to sort of lead the way, and that's kind of what made it happen.
Very good. So, the research that you do now, is there any particular equipment that you need for that that's specific to that type of research?
There's lots of equipment that you need, from little handheld pipettes to big centrifuges, things that spin very fast.
Mm-hmm.
But one of the changes in biology over the last couple of decades is that there are now sort of core facilities on campus. So some equipment's so expensive, individual labs can't afford them. So now we have core facilities we can use here, and there are services you can contract to. So if you want DNA sequencing done, you could have it done here at UT, or there are companies around the United States, even in Korea, across the ocean, where you can send your samples and have things done. So that landscape, the technology landscape, has changed dramatically, both in that there are many things we can do now that we couldn't even imagine doing back when I started. also that you can get other people to do them for you. You don't have to do them yourself.
Mm-hmm. So can you tell us a little bit more about the research that you do?
I guess I'm interested in two things right now. One is genetically engineered viruses and what we can do with those. So we all know about viral vaccines. We've all taken them, whether it's measles, polio, things like that. And there are potential problems with a lot of the vaccines. Polio is my favorite example. Right? We don't have polio in this country anymore. When I was growing up, actually when I was born, which was 1949, polio was still a big scourge in the United States, and there were major epidemics going on. And as a child, I was subject to the first polio vaccine. So the first polio vaccine was a shot given in the arm. It was a Kills virus. It worked well enough, but they came along with a second one, which is the one you eat. And they introduced that in the 60s, and that's brought us to the point of eradication of poliovirus in this side of the world, but not in the Middle East. There are parts of the Middle East where, for political reasons, we can't get in there vaccinated enough, or impoverished areas too, vaccine coverage may not be high. And the vaccine that we're using, actually, it's a weakened form of wild poliovirus. Mm-hmm. So it's good enough for your immune system to build up a response, but it doesn't give you disease. But you transmit the virus. So when you eat it, you put it out the other end, can infect other people. So this virus actually causes epidemics if you get it into the right conditions. Mm-hmm. It worked in this country because we could provide high enough coverage that it wouldn't start epidemics. But when you get into areas where the vaccine coverage is low, then the virus can go from, the vaccine can go from person to person. It evolves back to high virulence. It starts epidemics all over again. And so now there's just all kinds of cases where the vaccine has given rise to new circulating poliovirus that can cause disease in the Middle East. Genetic engineering allows us to remake the poliovirus so that it's weakened enough to use it as a vaccine, but it also can't evolve back up to high virulence again. So these are the types of questions I think about. How can we engineer viruses into vaccines, or maybe to actually engineer viruses to, if we wanted to control other species, one of the best uses is something called phage therapy, which is my other interest. So bacteriophages are viruses that kill bacteria, so we don't have to worry about them escaping and hurting people. They were the first actual proposed type of antibiotic, I think, back in the early 1900s. When they were first discovered, people thought, if they kill bacteria, we can use them, as treatments when we get infected with bacteria. And phages were tried at that time, but we didn't really know enough about them. Individual phages are very bacteria specific. So if you have a Staphylococcus infection, you might need a very, very specific phage for the strain you have. We didn't realize that back then. We do know that now. So phage therapy was popular in the 1930s and 40s, not that it was very successful. Then when antibiotics came in, antibiotics kicked everything off the stage, and we gave up on them. We gave up on phages. Now that we have all these drug-resistant bacteria, people are coming back to them. And so I'm interested in how can we make phage therapy work, and it's not as easy as it seems. You say bacterial viruses kill bacteria; they should be good as antibiotics, but there's actually a very sort of quantitative issue about how the phages grow on the bacteria, whether it's enough to actually control the population. Mm-hmm. So I'm studying sort of the processes that underlie success versus failure.
Okay, so the theory is that the viruses won't become immune to these bacteria?
It's actually much simpler than that. So, well, at least some of the problems are, you've identified one of the problems, which is could the bacteria become resistant to the bacteriophage? Mm-hmm. And they can do that. We know that. And that would cause failure of treatment. But treatment is probably more of a short-term process. So if you can, if you've got a growing bacterial population, you can knock it down 99%. That's probably good enough. Your immune system can take care of the rest of it. But whether if you introduce a phage to control a bacterial population, it may only kill some of the bacteria, not all of them. And so it's a dynamic process where you have to think about, okay, what's the rate at which the virus actually bumps into the bacterium, it sticks to it. When it makes babies, where do those babies go? And there are actually mechanisms of defense that bacteria have that aren't necessarily genetic resistant, but other types of things. It'd be, in a sense, almost like people wearing sunscreen to keep ultraviolet rays from getting to their skin, while bacteria can put things out on their surfaces that will at least slow down the rate at which bacterial viruses get into them. And so there are all kinds of ecological, epigenetic, and genetic issues in this. And so it's a fun problem because it's not obvious, but you can go into a very simple lab and study a lot of these basic processes.
So, do you have any advice for any future researchers that want to get into something like this?
Well, first of all, I wouldn't go, as an undergrad, I wouldn't go into any problem thinking this is the problem I'm going to work on for the rest of my life, right? You want to get experience doing research to figure out if you like it. The thing, if you do a quote research paper for a class, boring, not very exciting. It's not really what research is about. It's part of it, perhaps. But research is really about problem solving. It's about identifying problems, especially ones people haven't thought of before, and then it's about figuring out new ways to attack those problems. And that's the fun part, right? That's that's the sort of thing that keeps you awake at night, thinking, oh, what if I do this? So I would get some experience. You can do it at UT. UT is a big place. It's very intimidating when you're an undergrad. That was a good thing about Texas Tech, is it wasn't so intimidating, right? But any undergrad who wants to, who's persistent enough, can find a lab to work in. You got to be willing to commit time to it, right? You can't show up your last semester of your 4 or 5 year program and say, oh, I want to get some research experience on my CV. That's not the way to do it. You start early, you figure out what you're interested in, and then kind of fish around, find out who's doing what, try and get into a lab and sort of get into that experience of doing research. And, you should enjoy what you're doing. And if the lab's got bad dynamics, get out, find a different lab. But just start doing things. And then if it's not for you, don't worry about it. But follow your interests. Don't say, oh, I got to do research because somewhere down the road I'm going to need it. You want to get into it because I think I might like doing this sort of thing. I had an undergrad come to me, this was years ago now, said, I want to do lab work, like you work on phages or something like that, I want to do lab work. And I said, why? What's his major? Well, his major was math. And I said, why do you want to do lab work? And he said, well, I need to. And I said, no, you don't. And so we talked a little longer. Anyway, I set him up with a different colleague of mine. He did several mathematical projects with that person, got several papers out of it, got several awards, and because he got publications out and that, and he ended up doing what he wanted to do. He just was sort of had a misunderstanding that he thought he would have to do something he didn't want to do. But just follow your interests. But I would say of the people that come in, undergrads come in to work with me, something like a third of them actually work out. It takes a lot of time. You can't do research 1 hour a week, something like that. But for those, and several of them, I've had several pre-meds come in, and pre-meds really aren't, most of them aren't that geared towards research. So research is kind of it's a specialty, but you need to try it to figure out if you like it. But get started now. Don't assume what you're doing in class is anything like what doing research is about. There they're just two completely different worlds. Even though it's the same, the person sitting at the front of the classroom, might also be in the lab. What's being done in the lab just doesn't tie in at all to classwork. Classwork, frankly, is boring.
Okay. Well, thank you very much for your time.
Sure.